Hey everybody, this is Larry. This is Q4 of the weekly contest 221 maximum XOR with an element from array. So this was a problem during the contest that I to be honest, I feel like I've solved this before or a similar version, but I couldn't really figure out from where. And to be honest, I actually solved this in about 15 minutes during the contest, but but and I looked at other solutions as reviews after this, and it turns out that Python is just really slow. And because I wrote what I consider cleaner code for interview, it the performance was actually too slow. I think if I actually wrote stuff without using classes, this would have been fine. So let's go over that. And I actually spent an extra 15 minutes converting it to C sharp, but we're going to go over my Python solution. But and the C sharp version worked fast enough the first try. So I think that's a little bit unfortunate on the bounce. But yeah, cool. So the first thing that I would say is that when you see an XOR problem, especially maximum XOR, it's going to be greedy or in some way probably. This is just experience speaking. So also, speaking of greedy, hit the like button, hit the subscribe, and join me in Discord so you can ask me questions. Let me know what you think, because there might be a lot of questions for this problem. But yeah, so when I see XOR, the first thing that comes to mind is greedy. Why, right? Or maximum XOR. Why do I think greedy? Well, the two things. One is that when you look at the binary numbers, because if you do an XOR operation, all the bits are independent, right? So you have a binary number, all the bits are independent. When you want to get the max of it, you always want to greedily, your most significant bit, you want it to be a 1, right? No matter what, because if that's a 1, no matter what happens, that's going to be your max answer. Or like that's going to be bigger than anything that is on the other side where your first number is 0, right? So that's a property that I would think about. Okay, so then now I know that is greedy, I know that is maximum, and then there's this thing, right? Okay, how do we answer this? So there are actually apparently 2 ways to do this that I noticed. The way that I would think about it is that, okay, the way that we have these queries, I know that it's online. You're given an order and you have to do the result in order, but actually you can actually cheat a little bit by sorting it first, right? So I'm just very briefly. I actually recently did something similar on maybe a week ago, 2 weeks ago, where you answer the queries with if you build the prefix of the calculations, then you can answer those queries as you go. What do I mean by that, right? And I didn't code it this way, so I'm not going to talk about that. Or I don't have to code to show you per se. But but this is what I call the offline queries. Because why is it called offline? Because you know all the queries in advance, so you can do this offline, right? The way that I actually solved it during the contest is called online, right? Because what I did was that, okay, given this answer, I actually do not I do not know anything about the other answers, and I do not actually reuse things based on that knowledge, right? So what I mean by that is, okay, well, first of all, if you look at the problem correctly or like carefully, you have this m inside the query where, basically your m will, if you sort it in a way such that your m goes up, well, your tree will only mutate as that m goes, right? So that you can, so if you think about invariance, the invariant is that whatever solution that you have, let's say we have some black box solution, and we'll go over this for sure. Let's say you have some black box solution where, okay, let's say we sorted the queries already by the m's, and what that means is that okay, because if you think about it, an m means that, okay, we only really want to consider for m is equal to 1, we really only want to consider, let me just make this bigger. We only want to consider the numbers that are 0 and 1, right? So we only process up to 0 and 1. And then next, the m is 3. So then now we had 0 and 1. Now we process the 2 and the 3 into whatever we're doing. And then similarly, once we get to 6, we process the entire thing. Similar here as well. Let's just say we sort the nums away as well, obviously. Well, 1, well, then that means that we process nothing. So this will probably be -1, and it should. Let's say we have a 3, that means that we process the 2 and the 3, and then the 4, we process the 4 as well. So basically, that's the idea behind the offline, is that when you do the queries in an ordered, structured way, you can process the numbers also in that same structured way, so that you just keep on building on top of it. So that's kind of the idea behind the offline algorithm. I'm going to go over the online algorithm, and it should be mostly the same, to be honest, except for a couple of easier simplification, which I'll point out later. So I'm going to go over the online algorithm, which is what I actually did, which is that, so on an online algorithm, we assume that the things that don't change is the numbers, the input array, right? So because this doesn't change, we should be able to pre-process this entire thing all at the same time. And that's basically the idea, is that we process this at the same, one at a time, or we process the nums away, the entire thing at the same time in the beginning, and then we're able to enter this one at a time, because there's no prior knowledge that, and why is this called online? It's because in theory, let's say you process this, you can actually later still with the same data structure be like, hey Larry, can you answer this query of 10 and 2 or something like that, right? And then you'll be like, okay, I can still answer it because I still have the pre-processing done. So that's basically what is meant by an online algorithm, and they both have actually the same complexity, roughly. The only thing is that if you do it offline, you will have to sort this array and also this array. So in that sense, the online algorithm is actually more optimal. But okay, I think I talked a lot about the difference between offline and online, but I didn't actually go over the algorithm. So let's go over it real quick. So the greedy solution is just, like I said, for every bit we take greedily the best on the most significant bit. So let's go over the code real quick. So with this solution, we want to build a try based on where the edge is, whether each digit is 0 or 1, and we process each number this way. So for example, for each number we add it to the try, and for each try, let's look at the add part. So we start at the root for the try. We start the root, and then we look at, and I do this backwards because we want to focus on the most significant bit. And what I mean by most significant bit is that, okay, if you have like a binary number like this, if you just go from the back up, that's not greedy in the right direction, right? You want to be greedy on the earlier bit, because no matter what happens, let's say even if the rest is 0, and here the rest is 1, we clearly prefer this number because this is always going to be bigger than this number, right? In binary. Hopefully that makes sense, and that's logic behind the greedy. But for now, we're just thinking about the try, and basically we're doing it one bit at a time. We're processing the try such that, okay, for each number that we're processing, okay, so we have a try, and then we just go, okay, or this is actually a binary try, so you could even think of it as going one edge, going 0 from one side and 1 from the other side. So basically what I wrote is that, okay, so I add an edge with that bit. If this bit is a 1, then I just go on, I add an edge with the bit of 1, and then if it's 0, then I add an edge with a bit of 0, right? And this is basic try stuff. Hopefully that makes sense. And just to go over it, because there is a little bit of a difference because I do it online, which is that for me, I actually keep track for each edge, the maximum number on that side of the subtree, right? And why do I do that, right? because sorry, I think so. Actually, this should be technically y min, the min number. Sorry, and the reason why I wrote max is because I misread the problem. And if you watch me solve it live during the contest, I actually was confused about why I was getting wrong answers until I converted to a min, and then I changed the signs of some stuff because I just misread the problem. So, but basically, I keep track of the min on that edge because that means that almost like in a forced contradiction kind of way, if you go down that path and the smallest number is around that path, will tell you whether it is possible to go down that path with a larger number, right? So basically what I mean is that, okay, let's say your query number is 10, but your edge, your minimum numbers on that edge is 11. That means that all the numbers that are on that edge, in that subtree, the smallest number will be 11. That means that if you have a 10, then you cannot go down this path because there's no numbers that goes down that path. So that's basically the idea about keeping track of the min on the edge, and hopefully that makes sense. I'm just thinking a little bit to see if I can explain this in another way that is clearer. But I think that's basically the idea, right? Is that we keep the track of the min for that subtree, because if your current number, because you're for this problem, you want to get any possibilities of, like if we go down that subtree, we want to know that it is possible to have a number that has a number that's smaller than the input number, right? So that's basically the idea about keeping track of the min. And then the has edge now makes sense in that, okay, first of all, we have to obviously have an edge. And if we have an edge there, we check that the smallest number on that edge is smaller than our query number, which is the m that we're looking for. And then the get edge is just getting edge. So that's basically my library for node. And then, as I said, add, we just go down 1 bit by 1 bit. We keep track of the x. And then the get max is going to be the interesting / greedy part where, okay, as I said, if we have a prefix of 1, no matter what happens to the suffix, it is still better. So then we basically want to optimize for 1, right? So given our current number, and this x is the input that we're given, is actually called x, which is like the number that we're trying to get the maximal XOR for. So here we go, okay, if the number is of 1, well, if this is of 1, and in the XOR case, if you have another 1, then it's going to be a 0, and you don't want that. So if this number is of 1, you want a 0 so that the XOR of those 2 digits will be a 1. So that's basically what my idea is, and that, this is the greedy way. So if it's possible, then we take an edge on a 0, and then the result will have a 1 in it because the 1 XOR 0 will be a 1. So that's why we have this here. And then we go to the next edge on this tree. Otherwise, we just see if we can go down the 1 path. In this case, the XOR on this digit will be 0, but it's okay. You have no choice because there's no edge otherwise. If neither of those edges exist, then we just return -1 because, well, then it's not possible. And then, inversely, if this current bit is 0, and then, to satisfy our greedy nature, we need a 1 on the edge. If we have a 1, then we just, then the result will be a 1, and we do the same thing. Otherwise, we'll take a 0 if we can, and then we move along. Otherwise, there's no edge, and we return -1. So that's basically the idea behind this problem. So this is the online version of doing it. Again, in this way, the add function is O of 1, kind of in that is O of 32, where 32 is log of 10 to the 9th, roughly speaking. I guess it's 31, but or 30 actually, but maybe I could have done that to be faster. But in any case, but yeah, so, and that is just the 10 to the 9th part. So basically is the log of that. So it's basically n log u in that case, where n is the number of numbers. So yeah, and here it'll be q log u for the same reason, because we look at it for each bit we run the query, right? So in total, this is going to be O of n plus q times log u, just to be clear. So time is equal to O of n plus q log u, right? And then the space is also going to be just n log u, for that reason, because we only pre-process the space for the input numbers. So what changes would I have to make this offline, right? Well, first of all, as we said, we have to sort numbers and queries. So at the very least, our thing will be n log n plus q log q plus, again, for each query n number, we will have to go through the log u bits, as we still use a try. So it's going to be n plus q log u. So it's strictly going to be slower. For space, it should be the same. So it'll be n log u, unless you want to count sorting, unless you want to count sorting the q arrays and the n arrays, then maybe then, because technically then you're modifying input. So so that's the space for the offline version complexity, and the online complexity is this version. So how would you do it offline, right? So offline, as we said, you sort this and then you sort this, and then for each query, you basically process the numbers, you add it to the try, so that you add it to a try if the numbers are smaller than the m that is in the query. And that's pretty much it. The only thing, all the code will look about the same. The only thing that's different is that you don't have to do this edge min thing. You don't have to do this check, and therefore you don't need to keep track of it. So maybe it's a little bit easier in that way to write this part of it, and it's easier in terms of proving it, in terms of invariant, because you just bring the tree, knowing that the tree, or the try, sorry, knowing that the try will only have numbers that are smaller than m, so then that invariant will be true no matter what, right? So that's basically how I explain Q4. Cool. Let me know what you think about this problem. It was okay, but like I said, unfortunately in Python it was too slow. But I wrote the same code in C# and it passed. This is roughly my C# code. It took me an additional 17 minutes. So I'm a little bit sad about that, but yeah, that's all I have for this problem. Same complexity, obviously, for C#. Let me know what you think, and you can watch me solve it live during the contest now. This was a hard contest still. I still don't know how to do this one. I had to think about it. XOR. So this is a try problem. Annoying but doable, I guess. little rusty about it, to be honest, so this may take a while, but I solved this. On code force at some point. I'm just thinking about how to do this for solving it. So at each node of the try, what do we want to do? To get the query. That is the minimum element. Doesn't make sense, does it? On a path. So maximum on the path. I think that makes sense. Okay. I don't want to write this. This is so yucky. It's all implementation. Let's see. Let's add X. The most significant bits first. Okay. 1 is 0, 2. This is a little bit yucky, but silly mistakes today in general. This is a 0, so this is a 1. Okay, fine. Not close. What is that? I expected that, but okay. I messed that up. That's all. Okay, I think I got it. Well, I mean, might still be wrong, but yeah, it's still wrong. How do I even get 7? Is a -1, right? Nope. Oh, is it smaller than or greater than? Whoops. Oh, I messed up. Okay. How do I change it? Do we still have to get the max number? Yeah, okay. Don't know if this fixes it though. have any prints? Come on, please. Don't be too slow. How can it be too slow? It's just... I mean, it's only too slow. It's only too slow because of Python, I think. This is so silly. Because it's just 32 times 10 to the 5th, which is should be fast enough. I don't get it. I'm just looking at my Python go say I could optimize anything constantly. Not really. Nor should I really need it to be. So that's a little bit unfortunate. And 40 people gotten it already. So I think there are a lot of people who finished this contest already. So okay. This is so annoying because I'm basically spending the time rewriting this problem or rewriting the solution, and my C++ has been. Let's see. I haven't done tries in C++ in a while, so that's why. I could do in Java. Don't know if I know enough Java. Is that one? Oh. Okay. I haven't done C++ in a long, I haven't done this in a long time, so C# in a long time. I hate this. Hate every bit of this. Let's do. And I didn't even finish Q2, so this is just a mess. This is so stupid. Oh my god. I'm just so unhappy about this. I'm trying to also not use dictionaries, that's why. What am I writing? I forgot to see my colons. Huh? Why is this not compiling? Oh, this is not long. I don't know anymore. Okay. Okay. Doing this now. I mean, this is ridiculous. Can we do better than linear time? So. It'll be funny if this is also too slow because I actually don't know how fast C# performs on Leetcode. I actually didn't think about it at all. So that would be really sad. Oh no. 64. Oh my, I hate everything. I hate everything. 64. What? What am I doing? I don't remember that's quite right. Something like that though. 1, 2, 3. Okay, the other one, 79. Now my computer is being slow. Yes, of course, why not? Come on. This is not the time for my computer to be slow. I didn't think this would be the part I'm having issues with, to be honest. But okay. I'm being dumb. Really? If this is too slow, I'm gonna be unhappy about it because I spent half an hour on this. Hey, yeah, thanks for watching the video. Let me know what you think. Hit the like button, hit the subscribe button. Have a happy new year, and I will see you next time. Bye bye.